Programming robots is complicated due to lack of plug-and-play modules for skill acquisition. In this work, we present a novel robot inference and learning as a service platform, RILaaS, that virtualizes the deployment of deep learning models for real-time, accurate, and low-latency inference serving under variable Turing load. ReLOSS abstracts away the software and hardware dependencies from the robots and leverages upon the advancements in cloud and edge computing to meet the service level objectives of the application. Robots as a service model is growing rapidly, as seen from these recent articles by various media partners. ABI Research predicts 1.3 million installations of robots as a service in the next 6 years. The growing popularity is largely due to the potential flexibility, scalability, and lower cost of entry than offered by traditional robotics programs. The service model enables companies to offer automation by providing cloud-based subscription services in various industrial and service markets. The applications range from patrolling robots to providing on-demand automation in factories and warehouses, such as for e-commerce and online retail applications. The service model, however, relies on developing autonomous robots that can be flexibly programmed to perceive and act in new environments. This remains a challenge for robots of today, thereby limiting their applications to pre-programmed behaviors, often taught with teaching pendants or hard-coded with offline simulators. Learning-based approaches provide a feasible alternative, but the high sample and time complexity of learning new tasks makes it difficult to scale. To address these challenges, we present ReLOSS, a novel user-based platform for serving deep learning models to facilitate robot programming of new skills. Using the platform, we can readily deploy deep learning models in a plug-and-play manner on new robots in a scalable manner, while removing any custom middleware dependencies. Recent advancements in deep learning have led to a rise of robotic applications that rely on computationally expensive models for perception, planning, and control. Typical deep learning model involves training, adaptation, and inference stages. The training stage involves estimation of model parameters on large-scale data. Adaptation is the process of transferring and fine-tuning the model to a new environment, while inference involves predicting the model output for a given input. The inference stage decouples model from applications and must be done in real time to meet the performance requirements of the application. A number of challenges emerge in inference serving of a wide variety of models and applications. Supporting prominent machine learning frameworks such as TensorFlow and PyTorch is challenging because of the conflict in dependencies. We provide heterogeneous support in ReLOSS by using Docker containers to separately process each model. We facilitate rapid deployment on new robots by only requiring the public SSH key of the robot for authenticating and subscribing to the required models. As transmitting sensitive data over untrusted wireless networks is vulnerable to data infiltration, we use a fog robotics approach to place low-sensitive models on the cloud while using the edge infrastructure for more private data. For scalable workloads, we optimize the inference serving times with dedicated GPUs to meet the service level requirements that may not be possible with only using limited onboard storage and compute resources on the robot. Inference serving is emerging as an integral part of deploying deep learning models to meet the tighter latency requirements with more users and the networks getting more congested. A number of these services have emerged in the last couple of years to handle scaling, performance, and lifecycle management issues in production. Most of these services are optimized for serving specific kind of models and rely on the resources in the cloud only to meet the service level objectives. Moreover, creating and updating models on the back end is mostly manual and cumbersome. While cloud robotics provides scalable resources for compute and storage, the variable latency, that is the time required to send and receive a request, along with the security and privacy issues of sending confidential data over untrusted networks, make it difficult to meet the performance requirement of robotic applications. Fall robotics distribute the storage, compute, and networking resources between the cloud and the edge in a federated manner, thereby using the nearby resources to satisfy lower latency requirements while keeping the information within the trusted infrastructures to preserve the security and privacy requirements. ReLOSS exploits the resources in the cloud, edge, and fog continuum to optimize the inference serving requests under varying query load. We observe that the communication time varies from hundreds of milliseconds to milliseconds and microseconds as we move from cloud to edge along the continuum. The figure shows the overall architecture of the ReLOSS platform. Users can manage robots and models with a front-end API to upload trained models and deploy them on robots. The management server is responsible for storing the authorization policies and deploying the containerized models on inference servers. The front end interacts with the inference loop shown in green through a metric server, authorization cache, and a Docker model repository. The Prometheus server collects metrics about the model and the robot performance. The request interceptor authenticates the robot request with private SSH key and authorizes the use of specified model. The authorization policies are stored on a local Redis cache to minimize the network calls to a remote database in the AWS. The adaptive load balancer distributes the requests on inference servers in the cloud and the edge to meet the service level objectives of the application. We provide a user-facing REST API with the management server in Django to create and update models, data sets, robots, and metrics. The users can upload a new model or choose a publicly shared model from existing models where it is containerized and deployed to the inference server. The front end also allows the users to upload test data sets for querying the available models and visualizing the model outputs. Robots are added by specifying their public SSH key and subscribing to desired models on the front end. Models are added by uploading a folder containing the pre-trained model and specifying the input-output types and custom pre-processing, post-processing modules. Both models and data sets can be made public, private, or shared with selected users as per the application requirements. We provide a minimalistic robot client Python package on the robot end, using which the robot can specify the target address of the request interceptor, the model name and model version for inference, the private SSH key for authentication, and the SSL certificate location to encrypt the communication channel. Once the robot client object is created, the robot sends the inference request over gRPC and retrieves the target predictions with a simple function call. Inference requests from a robot or a fleet of robots need to be optimized for large-scale serving of deep models. Existing approaches make use of a priori estimation of inference times or some model selection strategy among ensemble of models to trade off between accuracy and latency as per the desired objectives. We use adaptive load balancing to distribute incoming requests efficiently across multiple servers to optimize serving of a large number of requests. Load balancing strategies supported in ReLOSS include round-robin, least connections, least model time, and Q-learning. We use engines for load balancing with round-robin and least connections, where the next queries are distributed sequentially or assigned to a server with least number of active connections. Both these strategies assume homogeneity of servers in processing the request. In least model time, requests are assigned based on running estimate of average round-trip latency, whereas for dynamic loads, we minimize the expected latency by optimally distributing the queries in a reinforcement learning setting. We formulate the inference optimization with reinforcement learning as an adaptive load balancing problem where an agent is assigned to each model to distribute the incoming queries. Each model is assigned to an agent that keeps an estimate of each server in an MDB tuple, where the state corresponds to number of active requests of a given model and the total number of active requests of all models for each server. The action corresponds to choosing the appropriate server index, and the reward function optimizes for the round trip latency time in serving the request. With a small probability, a server is randomly chosen to explore the state action space. The agent learns to choose the server such that the expected latency is minimized as estimated by the queue function in a given time horizon. Note that we assume the location and number of servers to be fixed in case the number of servers change, as in auto-scaling of cloud instances with more traffic. The load balancing agent needs to be retrained. We evaluate the ReLOSS platform in a vision-based decluttering scenario where a robot or a fleet of robots need to pick objects from the floor and deposit them in the target bins. The robot perceives the state of the environment with an RGBD image. It queries the object recognition and grass planning models to select the most likely object to be grasped and deposit them in the target bins. More details of these models can be found in the paper. We are interested in training these models in simulation with publicly available object meshes for scalable data collection and adapting them to the physical environment in a sample-efficient manner. In the first stage, we train the models in the simulation environment. In the second stage, we adapt these models to the physical environment with domain-invariant adversarial learning, and subsequently deploy them in the ReLOSS platform for low latency and high bandwidth serving on a fleet of robots. We perform experiments to empirically investigate the effect of resource placement of models on cloud versus edge, the effect of varying batch size and number of robots in the network, and the effect of simulated dynamic load profiles on inference optimization with adaptive load balancing. The resource placement experiments indicate here that deploying models on edge can reduce the latency times up to a factor of 4 with much less jitter. The communication overhead with edge serving is of the order of 100 milliseconds only. Moreover, the authentication time only takes 1 millisecond on average in comparison to 600 milliseconds for querying the relational database in AWS. We make two observations by varying the batch size and number of robots in the network. First, the latency scales sublinearly with batch size and number of robots. Second, the resource placement effect is prominent when computation time is much less than the communication time, as per the case of the object recognition model. In case of graph planning model, the resource placement effect is less dominant. ReLOSS gives comparable performance to TensorFlow serving for object recognition model deployed at the edge. Note that the TensorFlow serving does not provide custom preprocessing to support a wide variety of models, such as that of graph planning in this work. We next simulate time-varying requests of different profiles to evaluate the adaptive load balancing under dynamic loads. We query the object recognition and the graph planning models alternatively at specified rates to simulate the decluttering setup and compare the Q-learning-based adaptive load balancing with round-robin, least connections, and least model time strategies. We observe that Q-learning scales better with dynamic loads by optimally distributing the incoming requests. Least connections performance is better among the fixed load balancing strategies, and its performance is similar to Q-learning for lighter loads. The video here shows the resulting performance of the deployed models on the Toyota HSR robot. The robot queries the object recognition and the graph planning models with the RGBD image as input, and subsequently puts the object in the target bin. A number of directions have emerged from this work. First, we plan to couple the digital twin or simulator for continuous evaluation of the models. Moreover, optimizing the model's placement in addition to queries can be useful for meeting tighter service level objectives. Finally, we would like to adapt these models locally on a fleet of robots with federated learning. Please visit the project website for more details and testing of the RILaaS platform in serving the deep object recognition and graph planning models. We welcome further questions and collaborations.